So now that we've talked about async tasks, their methods, their structure, shown an example, let's go ahead and wrap up with some discussions about how to use async tasks effectively. So as we discussed, async tasks allow the user interface thread and the background thread to communicate in a clean way without exposing lots of the details to you. In particular, the on pre-execute, on post-execute, and on progress update methods will always run in the context of the UI thread without you having to do anything to make that happen other than be aware of it and override these methods as needed. These methods are very strongly connected and kind of managed implicitly by the async task framework classes themselves, so they're not something you have to be responsible for. The user interface thread is where the execute method gets called, on pre-execute. The actual implementation, executing this stuff, takes place in the executor in the background, and the main thread then handles on progress update and on post execute. So it's kind of cool. All these lifecycle methods get done automatically. You don't have to worry about how any of this stuff works. So unlike the Hammer framework, which we talked about briefly, you don't have to directly manipulate threads, handlers, messages, runnables. You just focus on async task instances and overriding the appropriate hook methods as needed. The async task framework embodies key characteristics of any framework. So we have inversion of control. You can see that you call execute, and then things start to happen controlled by the framework. There's domain-specific structure and functionality, all the stuff here like message queues and thread pools and future tasks, all those kinds of things are embodied for concurrent processing. And it's basically providing you a semi-complete portion of an application. So it provides lots of code. The actual implementation is several thousand lines long, and all you have to do is just come along and subclass and fill in the blanks. So you at very least have to fill in the do in background hook method, but the other ones are ones for you to do. So it's largely complete, save for some hook methods that you have to implement. As we talked about before, async tasks has elements of both black box and white box frameworks. So the hook methods it has, like on pre-execute, on post-execute, do in background, those are all examples of white box framework elements. It's executor strategy where you can plug and play different thread pooling strategies. That's an example of a black box framework. So this is basically the template method pattern. This is basically the strategy pattern. And there are trade-offs between black box and white box frameworks. So as a general rule of thumb, it's easier to build a white box framework because you're leaving it up to the users to do a lot of the decision points about when and where to extend and override stuff. But that means the users have more work. So the users have a harder time, even though the developers have an easier time. Often the case. And that's because the users being programmers, the programmers of the framework, have to know how to assemble the pieces of the puzzle together to make a complete puzzle. Black box frameworks are generally a little harder to develop because you have to anticipate things. You have to decide in advance like what the APIs are in a much more direct way, in a much more comprehensive, thought-out way. But they're often easier to use because you're basically just doing plugins. And so plugins are often a lot easier to use than knowing how to subclass and override the right things and so on. Async task uses a bunch of gang of four patterns. So template method is used for its white box capabilities. You extend things and override them, as we saw before. Strategy is used for its black box capabilities. Facade is used to simplify access to the whole Java executor framework and all the internal details of how things work under the hood. So these are all things that are handled for you by the implementation of the async task. You don't have to know about those things to use it. It also uses several pattern-oriented software architecture patterns. This is the book I wrote years ago, almost 20 years ago now, that focuses on concurrent programming. So it uses something called the half-sync, half-async pattern in order to coordinate between the user interface thread, which is kind of the half-async part, and the background threads, which are kind of the half-sync parts. So you might want to take a look at this pattern. It's also in the book. And the async task framework basically has the UI thread being the asynchronous portion, and then the threads that are in the pool of threads are kind of the synchronous portion, and that queue that's used to mediate access between the two layers is the queuing layer part. So that's kind of cool. And it also uses another pattern from the POSA 3 book called pooling, which is used to manage multiple instances of threads. And this allows, of course, pools of threads to use without having to recreate them from scratch each time. There are some traps and pitfalls with AsyncTask. One of the problems is that cancellation is voluntary, just like for regular threads. So you have to write your code to know how to be shut down properly. There are dependencies on an activity. So if you have strong references to an activity that's inside the AsyncTask object, you can have memory leaks. And I won't go through that in detail, but you can read about it here if you want more details. That's why I put that weak reference field in my AsyncTask implementation in the GCD AsyncTask example we looked at. If you don't play your cards right, then when you rotate stuff, if you make your AsyncTasks be destroyed when an activity goes away, then you may lose results or lose state. And so the way around that, of course, is to use that retain state or related state class that we showed. And then there's also portability issues, and this is absolutely maddening. Different versions of Android have different semantics for AsyncTask. So the original version, everything was executed serially in a background thread. From 1.6 to 2.3, they had AsyncTask run things in parallel, but that broke a lot of code because people hadn't expected that to happen. And then in Android 3.0, which is called Honeycomb, until now, they went ahead and changed the semantics back to these semantics, but if you want parallel computation, you can use execute on the executor. So just an example of semantics gone awry, semantics gone wild. There are various ways to address these issues. You can do this thing called the model view presenter pattern, which is very common with Android development. So you don't put the logic, you carefully separate out the data from the presentation from the computation. And then portability can be addressed by using patterns and APIs that relate to Android. So a good example is you supply the thread pool and use execute on an executor, so you get consistent semantics no matter what version of Android you're using. Having said that, nobody these days is using those older versions of Android. So if you want to release new versions of apps in the App Store, you have to be migrating to newer versions of Android. Google's moving much in the sort of Apple-like direction with respect to forcing the whole ecosystem to upgrade en masse when new releases come out. And that's largely driven by security issues. OK, so that's the end of the AsyncTask discussion. Hopefully that was useful to get the big picture view of how all the pieces fit together and how to use them effectively.